Molar enthalpies of formation. So we have been looking at the molar enthalpy of a reaction, but every compound that's formed from elements has its own molar enthalpy. Okay, this is a formation reaction. When we take oxygen and hydrogen and we combine them together to get water, that is an element plus an element gives us a compound, which is a formation reaction. Okay, we know that. We are smart people. Except I don't know what end of the felt to use. So if I was to take magnesium and react it with oxygen, what would my compound be? Oh, we're going to make this more complicated than that. Okay. If I take magnesium and I react it with carbon and I react it with oxygen, what kind of compound could you hazard a guess for? What kind of product? An element plus an element gives us one compound. What do you think we could build? Close. We would build magnesium carbonate. Now, we need to balance this puppy out. What's the trick?
3/2.
Well, because it's going to take this many oxygens, right? We have 2 oxygens here and 3 oxygens here. 2 times 3 is 6. So now that my oxygens are balanced, I need to balance my carbons. Yeah, you can, but we aren't going to. And then how many magnesiums? So 2, 2, 3, 2. Okay. So every compound has a standard molar enthalpy of formation. And if you were to open up your hot little data booklet to page that's electrodes, that won't work. Page 4 and 5. Tell me something that you notice about this table. There's a lot of numbers. Molar enthalpy of formation at, which is what Celsius? 25 degrees. So this is at room temperature. Okay. What if you, so on here, do we have magnesium?
Sorry, at the bottom of page 4.
Magnesium? No. What about carbon? Yeah, magnesium carbonate is there. Carbon's not there. What about oxygen? Elements are not in this table. Only compounds. Okay. Okay, so it's going to represent the amount of energy required or released when 1 mole of compound is formed from the elements. So there are some common compounds listed and their corresponding molar enthalpies. So if I wanted to look for this product, what would their delta? And notice the delta changes to this, delta FH. Remember before it was delta RH? This is delta FH. This is a formation. The other one is just reaction. What is this guy? So it's a hydrocarbon. And if I have CnH2n plus 2, I'm dealing with an alkane. An alkane. So what do you call this? How many carbons are there? 3. So this is propane. .103 what, Riley? And then notice at the top of the page, it gives you the units. What are the units? Well, kilo what? Kilojoules per mole, right? This is a molar enthalpy. This is standard molar enthalpy. When we see molar, we know that we're dealing with kilojoules per mole. Okay? And so how would we make this? If our product was C3H8, how would we make it? What element plus what element would make this compound? C plus, just like that? Why does it have to be H2, Sean? Because it's diatomic. Bromine isn't a gas, it's a liquid, and it's diatomic. Okay, so now we need to balance this out. And then we could say plus 103.8 kilojoules per mole, because this here indicates that it's exothermic, which means that our energy is going to go on our product side. Okay? All right. So if we were to do the reverse reaction of a formation, so now we've got a compound going to an element plus an element. What do we call that kind of reaction? Decomposition. Okay? So if we had the formation reaction, I'm just going to write this. Formation reaction. We took hydrogen and bromine. And I know that I just said bromine is a liquid. It's a liquid at room temperature. Same as mercury. It's a liquid at room temperature. What is the delta H of this, do you think? Actually, first, we're not done. We have to balance it. So, Declan, can you do that? Oh, look, BR2. Yes. I just had that conversation with Sean and then forgot to do it myself. Bromine is diatomic. Nope, there's just a certain, like fluorine, chlorine, bromine, iodine, hydrogen, and then carbon or phosphorus is 4 and sulfur is 8, right? Okay, let's open up our book and let's look at hydrogen bromide. Okay. Actually, that's not true. This is delta FH. Is negative 36.3 kilojoules per mole. But if I wanted to find the delta H of this reaction, I would have to go negative 36.3 and multiply it by the 2 moles, because this reaction actually produces 2 moles of hydrogen bromide. No, I'm doing this first. We're going to get to decomposition. So we're going to get what? Negative 76.2 joules. if we looked at the decomposition of it, yeah, didn't I write? Yep. Oh, I'm sorry. Okay, so decomposition is the reverse reaction of a composition or a formation reaction. So that means that my delta FH becomes a positive 36.3 kilojoules per mole because it's a reverse reaction. So my delta H is going to be positive 72.6 kilojoules per mole. Okay, all we're doing is we're just expanding on concepts that we've already learned. Good catch. Yeah, delta H is just kilojoules. That was my mistake. Okay, so we can use standard molar enthalpies to calculate enthalpy change for any given reaction using this following equation. Change in enthalpy is the sum of, right, this epsilon symbol means the sum of all of the products minus all of the reactants. And N is the number of moles from the balanced reaction. So here, how many moles of hydrogen bromide do we have? 2. How many moles of hydrogen do we have? And how many, not 0, 1. There's an unspoken 1 here. Oh, I thought I heard 0. Oh, sorry. Okay, and then how many moles of bromine? 1. Nope, the element is Br2, and there's only 1 mole of that in the reaction. Okay? And so delta FH comes from the data booklet. The other piece is that we need to know all of these reactions happen at SATP. SATP is at 25 degrees Celsius. Okay? Elements can't undergo a formation reaction. We can't take hydrogen. This is a poor example. We can't take hydrogen and form a diatomic hydrogen. In nature, it exists as H2. Okay? Under chemical reactions and pressure and all the other good situations, we can break it apart. But in theory, you can't take and form hydrogen. In theory, it's extremely explosive. Okay, let's look at this. The phase is also important. Look back at your data booklet, and what do you see? Look at water.
Oh, there's liquid and solid.
There's for water?
There's liquid and vapor.
And vapor meaning? So what is it if water is a liquid? Sorry, Haley, I didn't hear you. Okay, what about water as the gas? -0.8. Okay. You release less energy when you create steam than when you have water.
You won't ever see a water solid burning.
No.
That just is.
Yeah. Okay. Calculating enthalpy change for any given reaction using standard molar enthalpies of information is when you feel like you're missing some information and you have to create something. Okay? You need to have a balanced reaction. Hess's law is really helpful when calculating enthalpy change for a reaction and a list of intermediary reactions are given. So this one says calculate the standard enthalpy change for the following reaction. And this is all you get. Calcium oxide plus water gives you calcium hydroxide. What is the enthalpy change? Okay, so we know that delta H is equal to the sum of the N times delta RH for the products minus the sum of N times the delta RH for the reactants. And so when we look at this, delta H is equal to the delta H.
No, but it's N times. Is it delta F?
RF is the same. They're very interchangeable, but yes, we are talking about a formation reaction. Okay, so if I look at the products, I have one product, right? So it's going to be how many moles of calcium are there? Okay, so this is going to be N delta FH of calcium hydroxide minus N delta FH of calcium oxide plus N delta FH of water, that is liquid. That's what that means when it says the sum of. We're going to take these two products information and we're going to add them together, all within one set of brackets. Now we can do the filling in the information. There's 1 mole of calcium hydroxide in this reaction. And then what is the delta FH for calcium hydroxide?
Negative 985.2.
Do we agree with Riley?
Yeah.
So now, how many moles of calcium oxide are in the reaction? Calcium oxide. 1. And what is the delta FH of calcium oxide? Someone other than Riley. And then water, how many moles of water are there? And Declan, what's the delta FH of water as a liquid? How about 285? Would you settle for that? That's fine. Yes.
So the negative plus a negative is
It's got to be less than 1,000.
plus negative 3 like the negative 9.
Brackets, brackets, brackets. They are your world's bestest friend. Okay, negative 64.5 kilojoules.
Did you get that? I thought you said 64.
I don't know. You shouldn't get an 8. Because that's going to be a 7, and then 2 minus 7 is negative 5. He said he got negative 64.8. All right. Look at the second example. It says, use the following chemical reaction to calculate the molar enthalpy change for nitrogen dioxide. So, we know that molar enthalpy change is delta RH. So we're no longer looking for delta H, we're looking for delta RH. Delta H is equal to N delta RH. That's the formula that we can use. We have N, we have the number of moles in the reaction for each product or each compound. What we don't have is we don't have delta H. Okay, that's how we would get delta H. So what's my product? Nitrogen dioxide. So I'm going to take the sum, delta RH of NO2, and I'm going to subtract N delta RH of NO and N delta RH of O2. So how many moles of nitrogen dioxide are there? And what's the delta RH for nitrogen dioxide? Positive or negative? How many moles of nitrogen monoxide is there? And what's the delta RH for that, or delta FH for that? 33.2, yeah. Okay, how many moles of oxygen are in this equation? What's the molar enthalpy for oxygen? Perfect.
What is that last one?
0. What do I get for a value?
Negative 160.2.
That's my delta H. Now I can go back and I can solve for delta RH. Right? So how many moles, what are we looking for? This is for how many moles in the balanced reaction is there? Negative what? Okay, there's 8, 9, 10, 1, 2, 3. 6 questions. I will give you, let's do 12 minutes. Number 3, fertilizer urea, which is this big long piece with carbon and oxygen and NH2 in it, is produced along with liquid water by the reaction of ammonia and carbon dioxide. If the molar enthalpy change for urea is negative 134 kilojoules per mole, calculate the standard molar enthalpy of formation for urea. So what's the first thing that we have to do? We have nothing here. What's the first thing we have to do? No, not cry. You have to write a balanced equation before we can start with anything. So the question says that the fertilizer urea is produced by the reaction of ammonia. What is ammonia? And what does the problem say? Carbon dioxide. So we're going to make both of these a gas. And we produce what? You produce urea. Right here. Yeah. And
What's the state of the other one?
gases. Okay. What's it asking us to find? Okay, it's asking us to find the standard molar enthalpy of formation. What is this negative 134.0 kilojoules per mole? What is that? Right, of the reaction. If the molar enthalpy change for urea is negative 134 kilojoules per mole, so this is CONH2 twice, okay? Okay, how do we got to balance it? Okay, how do we make it in whack with hydrogens? Okay, why, Riley?
Because there's 6 on the product side and there's 3 on the reactant side. So you would times that by 2, and then that would also take care of your NH2.
Yeah, so here what Riley is saying is there's 4 hydrogens right here, and there's 2 hydrogens right here, so that's 6 on the product side. So how do we get 6? We multiply it by 2. That also takes care of this 2 nitrogen that we have. And this isn't cobalt, it's carbon monoxide. It should be a capital O, not a little o.
And then your carbons and...
And urea is actually a solid product. Sorry. Urea, farmers buy it. Okay, so I am looking for the standard molar enthalpy of formation. We're looking for delta FH. Okay. So delta FH is equal to delta H over the number of moles, right? That's how we find that. This is what we're looking for. The number of moles, this one comes from the balanced reaction. So then this delta H comes from here. Okay, and I just wrote it backwards because I wrote delta RH first.
Let's see, urea isn't on the list.
But it gave it to us here,
Oh,
right? Okay, so this negative 134 kilojoules per mole, because when we expand out this delta H, do we have delta H? Well, Eric just pointed out that we don't have the delta HF for urea. So what this we can do here, because this value here is from the reaction, okay, that 134 is from the whole reaction, not the formation reaction. So then we could go, there is 1 mole of urea from the reaction, and we could take this negative 134 kilojoules per mole, and this delta H for the whole reaction would be negative 134.0 kilojoules. So when we expand this out here, okay, do we see that expansion of the formula? We have the urea plus the water, because that's our products. And then we have the, oh, I wrote ammonium. Ammonia plus water. These are our reactants. And it's asking us the molar enthalpy of formation. So this one here, that's what we're solving for. That delta RH or delta FH. So what is the delta FH for water?
it's liquid, so it's 285.
What is it for ammonia? Yep, because it's liquid, Declan. It says in the problem liquid water. Oh, yeah. What is the delta FH for carbon monoxide or carbon dioxide? Okay. Yeah, we got 2 minutes. We can solve this one.
I thought no, I thought it was 130.
What? Yes, it still would be negative. You're right. And it's 285.8. I just decided to stop writing numbers apparently. Oh, I did something wrong.
You have to subtract.
Oh, hang on.
134 minus 485.3 plus 285. 333.5. Riley, I think your problem might have been minus 485. I got negative. Oh, that's fine.
Apparently, I don't know how to move signs over from one side to the other.
Oh, and that's what I did. I didn't put the 8 for water. 0.8. So it should be 333.5.
Yep. Are you not coming to Selfast, Declan?
Yeah, I'm coming to Selfast.
Okay, for homework, you need to complete page 383, 11 to 12, and practice problem number 4.